All right, so hopefully people can hear me. So I am unfortunately a phantom imposter. In fact, I'm a generally hydrodynamics imposter. I have never run a hydro code in my life. I have never looked at the phantom code. So therefore, you should take your lunch break early because I have absolutely nothing useful to tell you. This is a completely true statement. You really should take your lunch break early. Well, since I have the 20 minutes, I'll still, drone on for a while, but I won't be offended if you leave. Okay, so why am I here given that I don't know anything about SPH? Well, I'm interested in a few other things where SPH may well provide solutions to outstanding questions which we cannot answer in other ways. And so I should be listening instead of speaking. So some of the things I'm interested in are binary evolution, especially massive binaries. How do we get massive binaries to come close together? What are the channels? And I'll discuss this in a little bit more detail in a second. For massive binaries, for example, to form gravitational wave sources that LIGO can then observe. How do we form high mass X-ray binaries, like that object down there, Cygnus X1? How do we form, for that matter, low mass X-ray binaries, DX3 binaries, any kinds of combinations of things that involve the evolution of massive stars. Also interested in, as mentioned previously, gravitational wave astrophysics in high energy transients, often actually also coupled to massive binaries, because massive binaries are great ways to, for example, form kilonova through their mergers and gamma ray bursts. I'm very careful not to say any more short gamma ray bursts, because now we know that some long gamma ray bursts can also come from binary mergers and their afterglows, and some astrostatistics, and a few other things like dynamics and back of the envelope calculations. And although it is absolutely true that I've never run Phantom, I have, through the generosity of people like Mike and Rio and Daniel and David Liptai, got to play a little bit indirectly, vicariously, to enjoy some of their work on things like tidal disruption events and common envelope modeling with Phantom. And so I'm going to try to say a few things that I think I've learned from their generosity and these experiences. And I think one of the things that I've learned, and I realize I have to say this very carefully because I have a whole audience of people who are going to be very annoyed at me if I say this badly, but I have a feeling that sometimes we try to solve a very big problem because it's very exciting, but actually a very big problem has lots of issues. That's why it's so challenging, right? There are lots of spatial scales, there are lots of time scales involved, and sometimes, therefore, it's very hard to get a convincing result out. You're always concerned a little bit about your initial conditions, you're always concerned about your resolution. It's just an expensive calculation to do, so you can only do a small number of calculations, and it's hard to therefore appreciate what the impact of some of the inputs or assumptions might be. And so I'm wondering if actually sometimes we might, rather than trying to, for example, go for, let's solve the whole thing, let's do a TDE simulation from start to finish in all of its proper physics, maybe we should try to focus more on individual pieces of those calculations, because some of those pieces we actually can understand how to do roughly analytically. And if we do, enough individual pieces, maybe we can put them all together and get the bigger picture. So in particular, tidal disruption events. Okay, why are things so challenging? Well, for a very simple, obvious reason, which is everybody knows very well, right? That we have this situation that, let's say, if we assume that we have a sun-like star being disrupted by a 10 to the 6 solar mass black hole. Okay, standard beautiful pictures like this. I intentionally didn't take it from a SPH simulation because, as I said, I would feel like too much of an imposter. That's why I'm not showing any images from SPH simulations, but the basic point is, okay, this part of the calculation, right, we can all do analytically. Well, Martin Rees and Stroll Finney have done it analytically for us some 40 years ago, so now we can reproduce that calculation analytically. But we know what happens here, right? We know that the tidal disruption radius is something like 100 times the solar radius, right? If we have a mass ratio of 10 to the 6 to 1, and the solar radius sun. And so that means that the tidal disruption radius is actually about 10 times the radius of the innermost stable circular orbit. The apoapsis radius, meanwhile, even for the most bound debris, is about 1,000 times the ISCO radius. Obviously, we can't actually accrete from this kind of configuration, right? This material is happily flying around, and none of it is going to end up on the massive black hole. So somehow we need to find a way to heat up the material enough to change this, or somehow dissipate enough energy and angular momentum to start the accretion process. Now, once you start the accretion process, I think it's pretty clear that at that point, things are actually relatively straightforward, in the sense that once you start the accretion process, obviously you're generating lots of energy. You have significant outflows because you're pumping that energy in somewhere in an environment which is very optically thick, so you cannot radiate away efficiently. So you drive outflows, outflows collide with things, you have lots of shocks, and once that happens, you have your gas from these nice streams starts flaring all over the place, and that continues to feed into accretion. So that's all nice and at least intuitively understandable. But how do you actually start the accretion in the first place, I think, is a genuine challenge, because we know from observations like, for example, this one of 2019 quiz by Matt Nickel and collaborators, that in fact, if you look at the rise time, this is in Julian days, but basically if you look at the rise time, you see that it's 20 days or so, right? For this was a very nearby TDE, so you could actually capture the rise. This is telling you that it's sort of an orbital time scale, a single orbital time scale for the most bound debris, maybe half of that, right? So it's a very efficient rise. So that means that once accretion starts, it really has to turn on very, very promptly, right? And how to do that, I think, is a genuinely non-trivial question. It's of course very likely that it's coming, for example, from stream-stream collisions, right? So this was an argument posed by many people, and there have been some simulations of those stream-stream collisions by, for example, Liu and Bonnerod, that have tried to argue that those might give you sufficient flaring in order to then feed the gas. But I think that's actually, there are some challenges with that nonetheless. And so one question, before I get to this, I was going to make a slight apology. So the title of this particular paper that is taken from is "An Outflow Powers the Optical Rise of the Nearby Fast Evolving Tidal Disruption Event." And the apology is, I am actually a co-author on this particular paper, and really I'm a little bit uncomfortable about the title, because an outflow doesn't power the rise. An outflow, once you have an outflow, that already means you're accreting, right? So yes, once you have an outflow, it's easy to continue with accretion and luminosity. But I think to power this rapid rise, right, you really need to start accreting in the first place, which already means you have to divert some gas towards the central black hole. And so, as I said, could be stream-stream collisions, of course. That's one possibility. But I think another interesting proposal, and this is actually not my proposal, it's a proposal of Yuri Levin, is that you might maybe have just a little bit of gas already in the vicinity of the massive black hole. Now, if I already have a little bit of gas in the vicinity of the massive black hole, new gas comes in and it interacts with the gas which is already there. And that can, in principle, you might take this new gas and be able to thermalize it, redistribute its angular momentum, essentially add it to this ball of gas that's going around the massive black hole, and continuously feeding it in, you can start rapidly accreting. Now, in principle, it all sounds very sensible because, in fact, there are actually some observational suggestions that TDs do happen in environments where there is already some gas present. So that sounds compelling. Now, you might say, well, if I feed in this very large amount of gas and I have just a bit of gas there, won't it just either just push through the little small low density cloud of gas around, or even rip it off altogether? And the answer is, well, what you have to rely on is the fact that at early times, the very leading edge of your returning stream actually has a very small amount of mass. So initially you're feeding things in very slowly, right? You're bringing in initially small amounts of mass per unit time. You, in principle, have the time to repurpose that gas and add it to the cloud of gas that's already there. And then you already have a larger cloud of gas there and you're adding more gas. So maybe that all works, right? And I tried to do this calculation back of the envelope and convince myself that, yes, it can work. You resolved the problem. Wonderful. But then I realized that I probably was making too many assumptions about, for example, when you have this initial stream, yes, it has a small amount of gas, but it's also very thin. How much of the gas does it really interact with, right? If I have this thin stream of gas, does it only interact with the sort of a tube whose cross-section is equal to the size of the incoming gas stream? Or are there enough instabilities, for example, there's some fingers that allow you to interact with a larger volume of gas, right? So I think those are the kinds of questions that could be answered with a more detailed SPH simulation. So that's one specific proposal. I think Daniel might already be looking at that. So because I see him smiling at the back, he promises me that there will be a paper on this resubmitted anytime now. It's only been a couple of years, so it'll happen. This was my way of reminding you. All right. Next step, moving away from tidal disruption events towards binary evolution. So here's a little picture showing what we think binary evolution, for example, leading to the formation of a double neutron star might look like. So by double neutron star, I mean either something in our own galaxy, like the Hals-Taylor pulsar, B19, 13 plus 16, or maybe like the double pulsar, JO737, or maybe one of those LIGO sources like GW170817, the one with the gamma ray burst and the kilonova and all the incredibly exciting science. But how do you actually form those double neutron stars? Turns out it's not so easy, because if you want to have a double neutron star that has an orbital period of only a few hours, which is the case for things like the double pulsar or the Hals-Taylor binary, and which you need in order for this thing to be able to merge within the age of the universe, because if the orbital period is more than a day, it's going to take longer to merge the gravitational wave emission than the age of the universe, right? So you will never get your gamma ray bursts and gravitational waves and all the rest of it. It's not so easy because the stars that give rise to neutron stars are, at their maximal extent at least, more than an astronomical unit in radius, right? And so you cannot bring this binary that close together, right? If you start out with a binary that's very close, right, naively you would imagine that when stars expand, they just have a merger, and okay, that's exciting, but maybe it looks like it gives you a luminous red nova of the kind that Mike mentioned at the end of his talk, but it's not going to give you a gravitational wave event. If you put them very far apart, okay, that's all fine too. You'll have two supernova, maybe you'll have a nice binary, but it's going to be an incredibly wide binary, will never give you emerging double neutron star. So you need sort of a pretty interesting configuration of interactions. When your primary expands, it'll probably start getting tidally disrupted by the action of the secondary. So that's your Roche-Loeb overflow from the primary to the secondary. Then you're left with a naked helium star and a main sequence companion that may have gained some mass. Your naked helium star collapses into a neutron star in a supernova. Now your secondary expands. Now at this point, maybe the mass transfer is not dynamically stable. So it's a common envelope event, which engulfs the primary. Of course, brings the binary closer together. This is not shown to scale. So now you have a naked helium star and a much closer neutron star. You might have another stage of mass transfer, so-called KSBB mass transfer, because your low mass naked helium stars expand again at the end of the helium main sequence, just like normal stars that then expand at the end of the hydrogen main sequence. That since this binary is already quite close, this might cause another episode of mass transfer. Eventually, your now ultra-stripped secondary will explode, perhaps in an ultra-stripped supernova, and eventually you get your double neutron star. So several mass transfer episodes happening here, perhaps 3, and they're all key to the survival and the properties of this binary. So what can we do in order to try to understand them better? Well, one question is, can we actually come up with better models of stable mass transfer? So the two big questions from the point of view of stable mass transfer are, how conservative is it? Meaning, how much of the mass that we rip off the primary ends up on the secondary? That's very important in terms of the mass growth of the secondary, but it's also important in terms of the orbital properties of the binary. The second question is, if the mass transfer is not completely conservative, how much of that angular momentum is from the binaries carried away by the non-conservative mass transfer? Non-conservative meaning some of the mass is just ejected into space. How much angular momentum does that carry away, right? Because we usually, when we think about how does the binary evolve as a result of mass transfer, we think of it from the point of view of angular momentum conservation, right? So we want to know how much angular momentum is being carried away when the mass transfer is non-conservative. Now, why would the mass transfer not be conservative? Well, at least 3 possible reasons. Picture 1, this is from Kippenhahn, Meyer, Hofmeister, 1977. What they did was they took a single star, main sequence star. Here's a 10 solar mass star sitting in the main sequence, and they started feeding it. They started feeding it mass, just dumping mass onto the surface of the star at different rates. So this line corresponds to the evolution of the star when you're feeding mass onto it pretty slowly. So you can see that, okay, it deviates a little bit away from the main sequence normally, but it basically looks like almost like a sequence of main sequence stars of growing mass, right? So if I very slowly add mass to main sequence star, it just looks like a main sequence star of the new mass. But of course, if I feed the star very quickly, I'm adding energy to the star. The star is not able to immediately radiate it away. And so the only thing the star can do is expand, right? So the star, these curves over here correspond to stars that are being fed at the highest rates. And at the highest rates, the star veers way off the main sequence, goes up and to the right in the HR diagram. So yes, it does become a bit cooler, but it also becomes a lot more luminous. And of course, it hugely expands. So if it hugely expands, remember, this is now my accretor, right, that's doing this, right? If my accretor hugely expands, then the accretor doesn't fit inside the source lobe either, right? So at some point, if the accretor expands too much, then I lose, that mass gets lost from the binary, right? So that's one way that I might lose mass from the binary. So for example, imagine my donor is an evolved giant, and it's donating mass on its thermal time scale, which is pretty short for an evolved star. And my accretor is still a main sequence star, maybe even a low mass main sequence star. So its thermal time scale is very long. So it's being fed out of a fire hydrant, and it can't drink out of a fire hydrant. So the only thing it can do when you're dumping all this mass and energy on it is it expands, right? If it expands too much, you lose mass. That's option 1. Option 2 is we're adding mass to a star. Let's say you might be adding it through some kind of an accretion disk. So you're mostly adding it equatorially. That added mass has some angular momentum in it. What do? You spin up the star. You spin up the star. It doesn't take that much mass to actually spin up a star to critical rotation, because the stars, for a typical star, let's say main sequence star, is gyration radius, which is the radius that goes into the moment of inertia, right? So if you define your moment of inertia as mr squared, then r is that r which goes into I equals mr squared. That's the gyration radius, right? Gyration radius is actually a small fraction of the physical stellar radius, right? So, okay, they're just saying that the mass of the star is mostly centrally concentrated. So that means if I add even a bit of mass on the equator, might only take a few percent of the mass being added to the star to spin up the star to break up. Okay, now my star is spinning at breakup. So maybe if it was a B star, for example, it becomes a B star, right? It actually might form a disk in the equatorial plane with emission lines, hence the name B star. But this star, which has now been spun up, right, it really doesn't want to accrete any more material because it says, look, I'm already critically rotating, can't take anymore. So something has to happen to this mass. Where does it go? Well, probably possibly gets lost, possibly carries away some angular momentum. Another example, okay, taking, again, I don't know why I said, sorry, this is the wrong reference that came from a previous slide, apologies, but this is just a picture of Cygnus X1. In this picture, we have a black hole over here that's accreting, and a black hole is presumably Eddington limited. So the accretion is generating energy. This energy is creating an outflow. That outflow is preventing the star from accreting further, the black hole from accreting further, right? So here are at least 3 reasons why your accretor might not like to accept all this mass. Would be nice to know how much mass can it actually accrete and how much angular momentum is carried away. Now, I realize that this may not be the right question for hydro simulations because one of the big problems is in many of these cases, you actually have too little mass. And in fact, it may not be so much hydro may not be quite the right question because the self-interaction of the gas is maybe not the most important thing here. And so, but I'm still curious whether at least some of these scenarios might actually be appropriate for a hydro model. One scenario that people have actually attempted to model in hydro, so this was some work by Morgan MacLeod, is the possible onset of a common envelope, right? Because at that point you're starting to, you're not quite dynamically unstable yet. You are already essentially dynamically unstable, but you're not spiraling in yet in dynamical time scale, but you're already putting a lot of mass onto your accretor. The accretor has this ballooning envelope growing around it, and maybe in this case you could actually try to do this kind of modeling. I know some people in the audience who I won't name except to say they happen to be named Rio, have some skepticism about how some of this work was done, and so maybe SPH might be a way to re-examine some of the conclusions that were reached, for example, by Morgan in his analysis. Now, speaking of common envelopes, of course, there's the start of the dynamical in spiral. I already mentioned that. There's dynamical in spiral itself. In a sense, that part is kind of the least exciting almost because, okay, you roughly know what's going to happen, right? I mean, you can write down your favorite expressions for Bondi drag and more or less, or maybe model it with a wind tunnel simulation, and you'll get reasonably consistent answers, right? So you know roughly on what time scale the drag is going to happen, and frankly, whether you spiral in over 4 orbits or 5 orbits, I don't think makes a great deal of difference, at least from the point of view of the final outcome of the system, right? So that part I'm perhaps less interested in. There's one aspect of it I am interested in, though, and let me mention that before I forget, which is how much mass actually ends up on the accretor. Because if you do this standard calculation of normal Bondi Hoyle drag, you conclude that for every e-folding in the size of the separation, you also get an e-folding in the mass of the accretor. Which means if during a common envelope phase, I'm going to have my binary get a factor of 100 smaller in separation, my accretor is going to grow by roughly that same factor of 100 in mass. Except we know that doesn't happen. Because if that happened, then our neutron stars wouldn't be neutron stars anymore. They would be 100 solar mass black holes, right? and we observe them as being neutron stars, right? And we're pretty sure that they went through a common envelope phase. So something is happening there. There are a couple of possibilities. So actually, Morgan McLeod and Enrique Ramirez-Ruiz, for example, have argued that that the accretion is a lot less efficient because there is the common envelope is, when we normally think of Bondi drag, we normally think of kind of a uniform gas in the wind tunnel and an object moving through it. But they argue it's not at all uniform, that the scale height of the gas is actually smaller than the Bondi radius. So because the gas is very stratified in our star, gas has larger pressure and larger density closer to the center of the star, lower pressure and lower density on the outside, and that scale height is actually smaller than for realistic configurations, the size of the Bondi radius. So that means that although drag is still efficient, they argue accretion is inefficient. But one of the problems is they can't really tell how efficient the accretion is because their resolution is nowhere near the physical size of the accretor, which in this case is the radius of the neutron star or the Schwarzschild radius of the black hole. In fact, by nowhere near, I mean they're about 5 orders of magnitude off, right? So that means that they have to wildly extrapolate to really see what's happening near the accretor. And so one question that I think is worth asking is, can we do some sort of a multi-scale simulation where maybe we can figure out how much angular momentum is being transferred into the vicinity of the accretor on large scales, and then looking at what's happening on smaller scales really close to the accretor, because one of the possibilities for what actually prevents the accretor from growing too much in mass is that you end up with a centrifugal barrier, right? If you have a disk or a torus with enough angular momentum around the accretor, okay, that is not going to let you accrete, right? It just sits there in place because it cannot move in because it has too much angular momentum and can't transport out angular momentum quickly enough because this whole thing is happening very rapidly. But the other possibility you can do is you can see, so this here I do show some results from Mike, and Mike is looking at here what's happening in the separation and what might be the final outcomes. And he has, in this paper from 2022, he looked at some different equations of state and their impact. But one of the issues is that, as you can see, some of these final separations are getting awfully close to the effectively a kind of minimal resolution radius, which is a sort of radius of the gravitationally softened potential that Mike has put in to replace his core of the accretor. And so things get really difficult to measure in this regime, and you might start asking, how much do we trust results when we're getting really close to this region? And so one question is, well, what if instead of evolving the entire thing, starting out at 1,000 solar radii, and therefore also needing fairly small time steps, etc., what if you just focus in on this innermost region, right? So Jamie Law-Smith had tried to do that at a similar time to Mike's work, just focus in on the inner regions, but that's still difficult. You have to make some assumptions, like you have to assume that the donor structure inside the location of the accretor isn't really changed very much during the accretion process, right? Because Jamie basically took the structure of the star from some MESA model, for example, in this region and said, yep, that's all we need to evolve. Doesn't matter what happens before that. Somehow the accretor just gets there, and all I care about is the donor structure in these inner regions. Mike fortunately says that probably that's an okay assumption, so that part is encouraging. Of course, there may be a bigger concern, which is that we may not really know. In any case, the initial MESA model may not be the right model to use because, of course, there's a thermal timescale mass transfer phase preceding the very onset of the dynamical common envelope, and then probably another thermal timescale phase following the common envelope proper, when we get to the radiative intershell sitting underneath the outer convective envelope, and this radiative intershell is being transferred on a thermal timescale. Rio has a nice paper describing this two-stage process. So I think there are still some issues there. And then the last one I'm going to mention is I put this in before I realized Mike was before Mike reminded me of results he showed me a long time ago, which I have completely forgotten. So sincere apologies to Mike for doing that. But Mike was mentioned the light curves of common envelopes, and indeed, here's a plot from a paper we had written a few years ago, which argues that in the era of LSST, we may be expecting hundreds of detections, or maybe a lot fewer, depending on how we actually go about modeling the light curves of luminous red nova associated with common envelopes and associated with stellar mergers. And the big problem is that the way that almost everybody models these light curves, in this case, this is a model taken from Natasha Ivanova and Stephen Jestem, which in turn is based on some models of Popov, which in turn is based on essentially Arnett's models from 40 years ago for type 2p supernova. And that's really, these Arnett models are kind of what everybody is using as sort of the basis for these kinds of light curve calculations. And the basic idea is very simple. You explode, you consider a one-zone model, you explode a, you basically put in a bomb of energy in the center. It, of course, it's very optically thick, so that energy cannot easily get out. So you have some interaction between diffusion processes and expansion processes. And okay, maybe you put in some recombination on top of that, because recombination might give you some extra energy. So Matsumoto and Metzger, for example, have done that. But is that really relevant here? Because that's a perfectly relevant thing to do for a type 2p supernova where all the energy is being injected in the center. Here, remember, common envelope, right? We start out on the outside, and the energy is actually being not injected from the inside out, but initially from the outside in. The first friction and dissipation of energy are happening on the outside, and you have some conversion to thermal energy already on the outside at the start. Then you put more energy in the center. So sure, there's a lot more energy in the center, but on the other hand, the stuff on the outside has a much easier time of it getting out. And so you can do a simple naive calculation, and you can actually conclude, or at least I concluded, I may have done it wrong, that the stuff on the outside will get out much sooner and will, in the end, actually contribute more energy to your bolometric luminosity, because the stuff that's slowly rising up from the inside, yes, there was a lot more stuff there, but there's such a long diffusion time scale that it, in fact, the total luminosity is the energy available divided by the time scale in which the energy can escape, right? And so there's actually less energy coming from the stuff being deposited deep inside than from the early stuff being deposited on the outside. And so I think that my suggestion would be for modeling would actually be to focus not on the full structure, but even if we do include, and I know that people are working on doing this, we include radiation transport into phantom, is to focus on the outer layers of the envelope and that initial early deposition of energy. Okay, I think I've gone over. Apologies, I'm done.
Does anyone have any questions? Yep, Mike.
Maybe just some comments on the last point. So it's not completely obvious or clear to me that the argument just based on calculating the diffusion time scale might be completely applicable. So because at the deepest parts of the spiral in the common envelope, you're injecting energy really fast and concentrated at the last bits of the spiral in that most likely the energy might be carried out through shocks instead. And also the material above the companion so also significantly expanded, and so I'm not sure what you've assumed for that type of material there.
So I think it's a good question of whether or not the shocks in this case, how successful they are from actually escaping from all the way from the inside. So I agree. It's a very good question. It's an absolutely valid question to ask, and this is why I think it requires more work. We've been, I think, chatting with Evgeny quite a bit about this over the last several months. But one possibility is that the energy is actually being deposited deep enough in the inside, the shocks don't actually manage to make their way out, right? That you have too much mass loading above for the shocks to escape. So maybe there is no clean shock breakout in this case. It's so, I mean, one of the things, of course, is, we should, the observational motivation for this, right? And the observational motivation is that we are seeing apparently, at least some of the luminous red nova look like double peaked structures with a bluer peak followed by a redder peak. So I think that initial bluer peak certainly might be consistent with some kind of a shock breakout. Still a question in my mind whether it's a shock breakout from the lots of energy being deposited deep inside, or the little bit of energy being deposited, not too far beneath the photosphere. But the other interesting point is that the time scale, I think, between the two is still worryingly small, in the sense that if you look at your typical models of how long an in-spiral, actually dynamical in-spiral lasts, you're talking about years, right? Whereas the typical plateau duration might be a month or a few months in the luminous red nova, right? And so I'm still a little bit concerned about the timescales here, and that's why that's sort of prompting me to think that maybe the timescales are pointing to the energy deposition, the outer layers being the more likely culprit.
Well, actually, if you zoom onto my plot, it's only just few years, but of course that's also dependent on the system that one simulates.
Yep. Any other questions? All right. In that case, then we'll break for lunch. Yeah, and then we'll